Okay, the squeeze theorem is interesting, but it's only used once or twice in calculus that I recall. Basically, here's what it says. It says that if you can show that you have this function f of x squeezed between two other functions, h of x and g of x, and that if you know that the limit of h of x as x approaches c is L, as well as you know the limit of g of x as x approaches c is L, then that must mean that the limit of f of x as x approaches c must also equal L. Now, I'm going to give you just a real simple example here of this. Okay, so let's call this function, this black function, g of x. Let's call this red function down here h of x. And this blue function in the middle, we'll call that f of x. Now actually, those functions actually do have a name. This is actually the function x squared. This is the function minus x squared. Okay, and this function, this blue function, is actually the x cubed function. But if you notice, as you go, if you look at an interval about 0, because I want to focus on 0 here. If you look at an interval about 0, you notice there's an interval around 0 where this blue function lies completely within the bounds of the black and the red function. So basically what that's saying is, see, we know, if we know that this black function as x approaches 0 goes to 0, and we know this red function here as x goes to 0 is 0, and since we know that this blue function has to be between the two near 0, then we know that this function must also go to 0. And so that's the squeeze theorem. So since we know the limit of x squared as x approaches 0 is 0, and we know the limit of minus x squared as x approaches 0 is 0, then since x cubed falls between x cubed, hang on a second, x cubed is less than or equal to x squared, but greater than or equal to minus x squared. So in other words, x cubed is trapped between minus x squared and x squared, and since this function goes to 0 as x goes to 0, and this function goes to 0 as x goes to 0, then the one in the middle must also go to 0 as x approaches 0. So that's the squeeze theorem. And the application of the squeeze theorem is actually to prove a couple of special trig limits. The first limit is, it turns out that the limit of sine x over x is equal to 1. Now, if you tried to evaluate this, as x approaches 0, sine x over x is equal to 1. And if you tried to evaluate this at 0, you would get sine of 0 on top, which is 0, and then on bottom you would get 0. So you would get that indeterminate form 0 over 0. So that indeterminate form doesn't mean the limit does not exist. It means we've got to try to figure out what the limit is. Well, I'm going to go ahead and tell you that this limit is 1. And also I'm going to go ahead and tell you that the limit of 1 minus cosine x over x as x approaches 0 is 0. So memorize these two limits. Okay, now I'm not going to prove both of them, but I'm going to go ahead and prove the first one for you. And it's kind of an interesting way they prove it. Okay, so here's what we're going to do. I've drawn a picture of the unit circle, so the circle with radius 1 that's centered at the origin here. Okay, and now what I'm going to do is I'm going to go out here to the point 1, 0, and I'm going to send a vertical line up through here and then that vertical line is going to intersect a ray coming out here at an angle theta. So I've got an angle theta here, and I've got a ray coming out here, and it's going to intersect that. Now, basically what that does is that gives me three pieces. So I have this big triangle. It has a base of 1. The base is 1. And the height is actually tangent theta. You can use basic trig and show that the height is tangent theta. So this big triangle right here has an area of 1/2 tangent theta. Remember, the area of a triangle is 1/2 base times height? Well, the base times height would be 1 times tangent theta, or just tangent theta. And 1/2 of that would be tangent theta over 2. So the area of that big triangle is tangent theta over 2. Okay, then I'm going to look at this sector here, right here, this sector here. Now the formula for the area of a sector is actually r theta over 2. Well, r is 1, so 1 times theta over 2 would just be theta over 2. So the area of that sector is theta over 2. And then I'm going to look at this little triangle in here where it just connects to where this line hits the circle, and so it's going to connect there, and then it's going to connect right here. Okay, well this point, using what you know about unit circle, is actually the x value is sine theta and the y value is cosine theta. Oh, I actually have that backwards. It's the x value is cosine theta and the y value is sine theta. But anyway, so switch that around. Okay, so actually the height here is sine theta. So this little triangle has a base of 1, but the height is the y value, which is sine theta. Okay, so let me put that in. Okay, so I corrected this. All right. Okay, now, so anyway, so the area of the smaller triangle is 1/2 of the base, which is 1, times the height, which is sine theta. So that's going to be 1/2 of sine theta, or sine theta over 2. Now, common sense, if you just look at the picture, tells me that the bigger triangle is greater than or equal to the sector, which is greater than or equal to the small triangle. So their areas must have that same relationship. Okay, so let's go over here now. Part 1. So we know that tangent theta over 2 is greater than or equal to theta over 2, which is greater than or equal to sine theta over 2. Now tangent theta is sine theta over cosine theta, so I can rewrite that first term as sine theta over 2 cosine theta. Now if I multiply each of these terms by 2 sine theta, and the reason I want to do that is because that'll give me, for the middle term, it'll give me theta over sine theta. Now what I want is sine theta over theta, not theta over sine theta, but I can get there. Okay, so if I multiply this by 2 sine theta, then here's what's going to happen. The sine thetas are going to cancel, the 2's are going to cancel, and so I'm just going to have 1 over cosine theta right here. When I multiply this by 2 over sine theta, the 2's are going to cancel, and so I'm just going to have theta over sine theta for the middle expression. And then when I multiply this by sine theta over 2, it's just going to give me 1 because I'm multiplying by the reciprocal. Now, if I flip each of these terms over, since they're all positive terms, if I flip each of these terms over, then the inequalities have to reverse direction. So if I flip this over, I get cosine of theta is greater than or equal to, and then flip this over, sine theta over theta, which is greater than or equal to, and then if you flip 1 over, you just get 1. So basically now I have this relationship. So in other words, I've got sine theta over theta trapped between these two functions. In other words, I've got sine theta over theta squeezed between cosine theta and 1. So now, let's see what happens. Alright, so now I can use the squeeze theorem. Since I've got this function trapped between these two functions, well, we know from our trig identities, or a trig property, that the limit of cosine theta as theta goes to 0 is just cosine 0, which is 1. And we know that the limit of a constant as theta goes to whatever is 1 is just a constant, so that would be 1. So since the limit of this is 1 and the limit of this is 1 and this function was trapped between them, then this limit must also be 1 by the squeeze theorem. Ta-da! We're done with that. Okay, I'll do a couple of these and then you can freeze the video and look at the ones that I don't get to. Alright, let's find the limit of tangent x over x. Okay, well, tangent x over x is 0 over 0 if you let x go to 0. So that's indeterminate. So let's see what we can do. Well, I can write this as the limit of 1 over x tangent x. So I can write tangent x as sine x over cosine x. And then if I rearrange, if I put the sine x over here, then I can write that as the limit of sine x over x times 1 over cosine x. And then I can break this limit up into the product of two limits. So here I have the product of sine x over x. The limit of sine x over x as x goes to 0. And then 1 over cosine x as x goes to 0. Well, this limit, remember, is 1. So this limit is 1 because of the property we just talked about. And then this limit, all you have to do is let x go to 0 and you get 1 over cosine 0. And 1 over cosine 0 is just 1 over 1, which is also 1. So you end up with 1 times 1 is 1. Okay, now this one here, one thing that students like to do is they think they can write sine of 5x equal to 5 sine x, and that's not true. So make sure you don't try to do that. What we have to do here is we want to get it in the form of sine theta over theta. So if I multiply this by 5 over 5, then the argument of the sine and this are the same. So I basically can read this as sine theta over theta. And as x goes to 0, then 5x goes to 0. So I've got the same action happening. Now factor this 5 out of the limit, and so I get 5 times the limit of this. So this is like saying sine theta over theta as theta goes to 0. So, and we know that goes to 1. So this is just going to be 5 times 1. Okay, which is 5. I used u, but you know, you could use theta if you wanted to. Alright, now both of these two, you'll get 0 over 0 if you try to evaluate it, so you get indeterminate forms. The first one, I just factored the top with difference of squares, and then I broke up this into 1 minus cosine x over x and 1 plus cosine x. So I broke the limit up into the product of these two limits. And this limit, if you go back and look up here, that limit, remember, is 0. So that limit is actually going to be 0. And then this limit is 1 plus cosine of 0, which is 1 plus 1, which is 2. So I get 0 times 2, which is 0. Now one more. This one I have sine plus 1 minus cosine x over x. Well, I can write this as sine over x plus 1 minus cosine x over x. So I can break that up into the sum of these two functions. And then I can break that limit up into the sum of the two limits. So I have the limit of sine x over x as x approaches 0, and I know that's 1. And then I have the limit of 1 minus cosine x over x as x approaches 0. And guess what? I know that one is 0. So that's just going to be 1 plus 0, which is 1. And that pretty much ends this lecture.